Have you ever wondered where everything you see, touch, and feel came from? The story of our universe begins at what scientists call a singularity, a point of infinite density and heat. Picture all the mass and space-time of the universe, everything that ever was and ever will be, crammed into a single, unimaginably small point. Now, imagine that point beginning to expand. This isn't just any expansion, but one happening at an incredible rate. This moment, occurring approximately 13.7 billion years ago, marked the start of an event we now know as cosmic inflation. But this was merely the prelude, the first note in a symphony of cosmic evolution that would eventually lead to the universe we inhabit today. And so the birth of our universe began with a bang, not a whisper. From a single point, the universe burst into existence. We're talking about an event of cosmic proportions, an idea brought forth by physicist Alan Guth in 1980. Guth proposed a theory that has since been a cornerstone in our understanding of the universe's birth, the theory of cosmic inflation. Imagine, if you will, the universe as a tiny, infinitesimally small point, a point so small, so dense, that it's almost beyond comprehension. Then, in a fraction of a second, faster than the blink of an eye, this point begins to expand. But this isn't just any ordinary expansion. No, this is an exponential expansion, a rapid stretching of space itself. Now, when we say rapid, we're talking about a timescale that's almost inconceivable. You see, this period of cosmic inflation lasted for roughly 10 to the power of negative 32 seconds. It's a time so minuscule that it's hard to imagine, yet during this tiny slice of time, the universe grew exponentially from a pinpoint to an astronomical size. This inflation set the stage for everything that was to come. It's like the universe was a grand theater and cosmic inflation was the opening act, setting the scene for the drama of cosmic evolution to unfold. It laid the foundations, creating the conditions necessary for the universe as we know it to grow and evolve. But why does this matter? Well, this period of rapid expansion is crucial for understanding not just where we came from, but also where we're going. You see, the effects of this inflation are still with us today, shaping the universe in ways we're still striving to understand. In essence, cosmic inflation is the bridge between the birth of the universe and its ongoing evolution. It's the link that connects the past, present, and future of everything around us. It's the key to understanding the grand tapestry of the cosmos. In the blink of an eye, the universe ballooned from a pinpoint to a cosmos. But what happened after the initial burst of inflation, you might ask? Well, let's delve into that fascinating period. The immediate aftermath of inflation was a universe continuing to expand, albeit at a slower pace. Picture it as a cosmic balloon, still inflating, but not quite as rapidly as that initial burst. As the universe continued to spread out, it began to cool. It's a bit like when you blow up a balloon and then let it go. The air inside cools as it expands. Similarly, the universe, once a hot, dense point of energy, started to cool as it expanded. Now, this cooling process was vital for the next phase in our cosmic story. As the universe cooled, it allowed for the formation of subatomic particles. These particles are the building blocks of atoms, the fundamental constituents of matter. We're talking about particles like quarks, electrons, and neutrinos, a veritable particle soup, if you will. As the universe cooled further, these subatomic particles began to combine to form simple atoms. And the universe's first atoms were those of hydrogen and helium, the lightest elements in the periodic table. The universe at this time was essentially a hot, dense soup of these basic atoms, interspersed with photons, particles of light. And let's not forget about the temperature. The universe at this time was extremely hot, around 10 billion degrees Fahrenheit. So imagine a soup that's hotter than anything we can comprehend on Earth. Yet, as hot as it was, this was significantly cooler than the conditions of the universe during the inflation period. This cooling and expanding universe set the stage for the next act in our cosmic drama. It paved the way for the formation of more complex atoms and eventually stars and galaxies, but that's a story for another time. What evidence do we have of this cosmic event, you might ask? Well, enter the cosmic microwave background, or CMB for short. This is essentially the universe's baby picture, the afterglow of the Big Bang, if you will. It's a faint cosmic echo that lingers from the early universe, and we can detect it with modern instruments. The CMB is a snapshot of the universe roughly 380,000 years after the Big Bang, when the universe had cooled down enough for atoms to form and light to travel freely. It's like a shimmering cosmic veil that covers the entire sky. And the coolest part, it's pretty much the same in every direction we look. This uniformity supports the idea that the universe experienced rapid inflation, expanding faster than the speed of light in its early moments. So, the CMB isn't just beautiful, it's also a powerful piece of evidence for the Big Bang theory. The CMB is a whisper from the past, a glimpse into the universe's fiery birth. Fast forward to today, billions of years since the Big Bang. The universe we reside in has continued to grow and cool, giving birth to a cosmic tapestry of stars, galaxies, and other celestial structures. From the tiniest particles to the grandest galaxies, everything we see around us is a result of the universe's expansion from that initial point of singularity. Stars, those glowing spheres of hot gas, are nuclear furnaces that forge the elements necessary for life. Galaxies, vast islands of billions of stars, trace a cosmic web across the expanse of the universe. But how do we know that the universe is still expanding? Enter the Hubble-Lemaitre law. Named after Edwin Hubble and Georges Lemaitre, this law observes that galaxies are moving away from us. The farther a galaxy is, the faster it's receding. This isn't because galaxies are moving through space, but rather because space itself is expanding, carrying galaxies along for the ride. So here we are, living in a universe that's been growing for billions of years. From a single, infinitely dense point, the cosmos has bloomed into a vast, intricate, and ever-expanding entity. It's a breathtaking thought, isn't it? Our universe, once a single point, now spans billions of light years and continues to grow. Yet, the Big Bang is not the only theory about our universe's birth. There are alternative notions that challenge this dominant perspective. One such idea is the theory of eternal inflation. This suggests that inflation never stopped and that multiple universes might be inflating simultaneously. Then there's the oscillating universe theory, proposing that the universe expands and contracts, much like a beating heart, in an endless cycle of big bangs and big crunches. Current research in cosmology, aided by state-of-the-art tools like the James Webb Space Telescope, is continually refining our grasp of the universe's beginnings. These studies delve deeper into the cosmic microwave background, probe the nature of dark matter, and explore the potential existence of other universes. Each discovery, each revelation, brings us a step closer to comprehending the vast cosmic puzzle. We continue to seek answers driven by our insatiable curiosity about our cosmic origins. The Big Bang theory is a testament to our quest for understanding. This monumental scientific concept stands as a cornerstone of cosmological science, providing the most widely accepted account of our universe's origins. From the infinite density of the singularity to the cosmic microwave background, every facet of the theory brings us closer